So, the hook for today ponders, what does voltage mean? Does low voltage mean low danger? And the answer is no. That a car battery, a 12-volt car battery, can easily electrocute you. And we're going to play around with the Van de Graaff generator, which is like running at 100,000 volts. You go to a child's birthday party and you take a balloon and rub it on your hair and giggle, giggle, giggle. It sticks to the birthday child. That was probably at least 5,000, maybe 10,000 volts that you were dealing with when you made that balloon stick to the child. So sometimes high voltage means danger, but sometimes high voltage is not dangerous. Well, goodness, what does voltage mean? So let's pursue that a little bit. I have here two locations which are both neutral. That does not mean they are without charge. It means they are without net charge, and we'll go ahead and represent that charge which would be there on that neutral object, and we'll represent the fact that there's charge on this neutral object. Now, the story thickens as I reach in with my electron tweezers and I grab an electron out of this location and begin hauling it up to the upper location. But the minute I get that electron out of this location, this then becomes to be positively charged. And so it's going to attract this electron. And so my hauling this up is going to be a matter of me exerting a force to overcome that attraction back to this positive plate, this now positive plate, and that force will act through this distance that I haul it. So you put down what that means. When a force acts through a distance, what's going on? And then I'll reach in and grab another one. Oh my! Now this plate is even more positive, and now the place I'm hauling it to is negative. So there's this definite force that I have to exert through a distance to get this up here. I have done work. And Mr. Houghton's definition, indeed, our definition of work in its most general form, went how? You can put that on your worksheet. And what is going on here is that I am pulling, if it was me with tweezers physically hauling these negative charges up here, I am pulling energy, chemical energy, out of my body, and that energy is becoming electrical energy that exists because of the difference between these two places. And we will speak of potential difference. And I should have had that already up here, but 72. Give us a break here. Potential difference. And what that name seems to be saying is that there is potential energy here because of the electrical difference between these two places. That if I were to go to this location and start circulating among the electrons, I would find that they're unhappy. They don't like being crowded in with other electrons. I said, yo, buddy, I know this place where there are 2 protons for every electron. And they're salivating. Yeah, yeah, tell me more. Yeah, I could get you there. Yeah, yeah, but you have to do me a little favor. Oh, yo, I do anything. All right. And so I provide this pathway. Oops, come on now. Boom. I provide this pathway from this place to this place, a conductive pathway, a pathway that charges can move along, and the charges stream away from this and go running through this. They're even willing to do work and transform their electrical energy into light and heat here in this light bulb. But clearly they want to move. That indicates that there was energy in that difference, and when I provided them a pathway, they do move. And they transform their electrical energy into light and heat as they come back down. Okay, so voltage. Well, one expression, and we're going to run into several, well, one other before we're done, but this idea of voltage is perhaps represented by potential difference. Please understand that I'll give you the actual definition of voltage in just a second. We need to understand that potential difference is more metaphor than actual description. It is like voltage is kind of like the potential energy that exists because there is a difference between the 2 places. And it could be that both of these, let me get rid of positive charge here. And I'll put an extra negative in. Oops, I'll get rid of another positive. No, that was a negative I got rid of. Boom. So that this location is negative and this location is negative. But if this location is more negative, we'll make it definitely more negative. That has a net 3 extra electrons, and this only has 1 extra electron. If this is more negative, then there is a difference, an electrical difference, and there would be energy in that situation. There would be a difference in voltage between those 2. So that is kind of what voltage is that it doesn't have to be between positive and negative. It could be between more negative and less negative, or more positive and less positive. But when there is a difference, you have this unique situation that we will describe as voltage. Here is the definition of voltage. Oh, it's not quite as nice, but one term that means the same thing as voltage is potential difference. Another term we will use is just the potential or electrical potential. We'll leave the word difference unspoken. But what we technically mean is how much work did I do, that is, how much energy did I transform, but how much work per coulomb of charge that was moved. So voltage is not energy. Voltage is energy or work divided by charge. And here we've got this AB. This would be this difference between location A and location B. And we would talk about the voltage of A relative to B. The difference between location A and location B. And it's equal to the work per charge moved. And then there's a negative here. And you're just going to have to trust me on that. It's going to make things come out right if we put the negative there. The units of voltage are volts. But you look at this equation here, if volts are the units of voltage, we use a capital V for voltage and a capital V for volts, the units and the idea, both with the same letter. But could you tell me what a volt is equal to in terms of other units, like these units. This question about danger, well, if there's a lot of energy involved, that's going to be a dangerous thing. With a 12-volt car battery, it's only 12 volts, but the amount of charge, the amount of current, the amount of amperage that a car battery can generate is very large, which means that the amount of energy is going to have to be very large, 12 times as large if this ratio is to 12. That's why a car battery is dangerous. Whereas when we work with the Van de Graaff generator, 100,000 volts, that's the potential difference between you and the Van de Graaff generator, but the amount of charge that will move might be millionths or billionths of a coulomb, and so the amount of energy here is very small, and that makes this not dangerous. You cannot look at voltage by itself and know whether a lot of voltage means danger or not. It also depends upon how much charge it's able to move. So it's complicated. Alright, let's take that definition of voltage that you just learned, and here is a AA cell. It's got a negative end that's here and a positive end up here with a little button. This is a 1.5 volt. What is that telling me? That this is 1.5 volts. At any rate, if we move 5 coulombs from here to here, how much energy would be involved? You do it. Next, I want to take this and fill in the blanks. That voltage, well, here it was. There was the definition of voltage. We need to know that and be able to work with it. But look, the W went away and I've got a D there. The W standing for work. What together with D is the same thing as work? You stop the show, put it on your worksheet, and then this quantity Q gets divided into this quantity. What is that equal to? You stop the worksheet, put them in, then start the worksheet and see if this is what you had there. That force dot distance is the same thing as work. And force divided by charge is the definition of field strength. Well, there is an interesting relationship. Voltage is somehow related to the electric field, dotted with the distance that you have moved through the electric field. That is, if this was VAB, as I wrote it in the previous with a subscript AB here, the potential difference between A and B, this distance here would be the distance from A to B. And I would multiply that by the field between A and B. And I would have to include a little negative, and that would be the voltage between A and B. I want you to look at this picture. This is the electric field. These 4 arrows represent the electric field. You can see it is a uniform field. The density of the field line stays the same, so it's an equal strength field everywhere. Here is A, and here is B, and the question first is, which one of these is at a higher potential? Higher potential means more positive. Lower potential means more negative. That if you are at a place, if you are at a location that is positive, and there's another location that is negative, A positive test charge put here would have a lot of energy. It would be repelled by that, it would be attracted by that, and it would tend to move in this direction, flowing from, let's get more color here, from high potential to low potential. Current, an electrical current, is moving positive charge, and just like a current in a stream, water current, they always flow from high down to low. So a location with high potential would be a positive place, and low potential would be a less positive place, or a negative place. Okay, perhaps it is no longer an interesting question, but where is the higher potential, at A or B? And then, if this field in here is this uniform 7 newtons per coulomb, and the distance from A to B is 5 meters, and the voltage here is 100 volts, what is the voltage here? That is, you ought to be able to use this equation to work out the potential difference between the two. And then the question is it that much more than 100 or that much less than 100? Good luck. If, new problem, the field at the top of your table is 15 newtons per coulomb upward. In fact, the field at the top of your table is probably more nearly 150 newtons per coulomb. Amazingly strong field around the Earth. And in reality, it's probably directed downwards. But suppose it was 15 newtons per coulomb upward. What force would a 3 coulomb negative charge placed on the table experience? You need to get the magnitude, but you also need to choose between up and down. This would be an application of the relationship between field strength and force, which if you don't remember, then you need to look it up. Do this problem. New